Okay, welcome to the April 2023 meeting of the Mornington Peninsula Astronomical Society. And shown here on the first slide is a few things that have occurred during this month. I won't be covering the eclipse if anyone's asking, but Mark will be doing a bit on that, and also I think Chris makes a mention of it in his segment as well. So, so starting actually down here at this one, tonight we have a 300 kilogram satellite that's re-entering somewhere in the world. It's a NASA solar observing satellite that was launched back in about 2002, and it's had communication difficulties, so it's on the way in and is due to come in either tonight or early tomorrow morning. And NASA's not actually releasing where it's going to come down, which is highly unusual of it to do that. And they've actually said there's about a 1 in 2,467 chance of it hitting someone. So that's considered to be a low probability, so they're not too worried about that someone might get hit by this thing coming in, or bits and pieces that are left over from it. Up the top here was a couple of days ago, on the 17th, Elon Musk's SpaceX so-called Starship was due to launch from the Star Base, as they call it, in Boca Chica in Texas, and got down to about, I think, 1 minute. Got down to about 1 minute from launch before it was actually scrubbed due to fuel valve issues causing pressurization in the lower stage. Now, in the left-hand image here, you actually see it before it lifted off. So there's a lower stage there and an upper stage. So unlike the Saturn V rocket, this one has 2 stages. And over on the right-hand side is not the actual launch itself, because they had to scrub it, but this was the test that they did back in February of the exact same lower stage. And there's a bit of a close-up of it. You can see the water deluge coming in to help cool things down when they fire it. This was only a test fire of about 10 seconds. And of the 33 rocket engines, only 31 were working on the day, so 2 failed, but 31 wouldn't have been enough to put it into orbit. And I believe the quote for it was that success was going to be if it actually made it into orbit. So they considered lack of success if it blew up on the launch pad, or a rapid unscheduled disassembly, I think is the term they would typically use. So this particular footage here, and you can see it's over and done with pretty quickly, but it was looking promising, and hopefully in the next couple of days, because the next launch window is on the 20th, which is tomorrow, and just before 11:30 p.m. our time. So assuming that it's on time, which of course rocket launches tend to be fairly not on time, but you never know your luck. But of course it's a late night to be up to watch it. When it does go up, assuming it does go up in successful manner, it will be the most powerful rocket ever built. So it will exceed the Saturn V that went to the moon in terms of thrust by almost doubling it. So quite significantly higher payload, and certainly more than the one that NASA was using to take Artemis to the moon. So in other words, it's significantly more thrust than that as well. So this is really designed as a heavy lifter to take a lot of payload up in one go. So pretty impressive. It's about 9 meters taller than the Saturn V as well. And you'd have to say you'd be pretty brave to actually be that close to it when it goes up, in case something went wrong. It would go bang in a very, very nasty way. Down the bottom right-hand side there, a rocket launch that was successful was the European Space Agency's JUICE mission. JUICE, or the Jupiter Icy Moon mission, was launched a couple of days ago, I think on the 14th, from French Guiana. And that's on its way to Jupiter now, and it will take 8 years to get to Jupiter. But when it gets there...
5, 4,
And this is the actual launch itself in French.
Top. Allumage Vulcain. Allumage AP, décollage. La propulsion est nominale.
So very cloudy on the way, on the launch.
La propulsion est nominale.
It's already underway. It'll go through a couple of gravitational loops to actually get to Jupiter. That's why it's taking 8 years to get there. But when it does get there, it's going to particularly concentrate on Jupiter, Callisto, Ganymede and Europa. It won't look at Io at all because that's a volcanic one. So this one is specialising in looking at ice worlds, and we'll be looking for signs of life with the most up-to-date instruments available as well. And then it will go into orbit around Ganymede. So it will be the first time a spacecraft has actually gone into orbit around a natural moon of a planet. So tonight I'll go through the events as we usually do, past month and upcoming month, and Mark will hop in with Sky for the month. Chris will do both the Astro Mo Pho and also talk a little bit about the members survey that was there a couple of months ago. Then we'll look at some really deep and meaningful existential physics with Sabine Hossenfelder. I know one of the people in the society is aware of her because of a post in E-Scorpius, I think, a couple of weeks ago. And then a little bit later we'll look at the post-mortem of the Arecibo radio telescope. That was the giant one in Puerto Rico that we showed on a meeting, or getting on for about 2 years ago or so now. And this is from the final report as to what happened to it, and certainly quite interesting. Then we'll close at the end with another parody, and this one's quite a good one about stellar life cycles. Right, so we'll begin this one with one of Phil Peters' videos that he took at the public viewing night, which you can see going in the background. So no expense spared at the public night. We had fireworks going in the background for the public as well. Beginning of the period, we had a birthday party here for an 11-year-old, Amy, here at the Briars. Then we had the Working Bee, and then Strathaired Primary School, who were on camp next door at the Briars, came in, and we gave them a talk, and they were fortunate that it was good conditions, so they got to see the night sky unimpeded. Had cosmology group, then committee meeting. Committee meeting looked at the wrap up of the trivia concert that we had several weeks ago now. Also looked at the survey that you'll hear about tonight from Chris, also finalising and chasing up the status of the marquee. And also it looks like we're hosting the next Vastrock in several months' time, because everyone else has run a mile in terms of other Victorian societies on that one. So we've got to get cracking on that and get that underway. 3rd of April, several members went up to see Brian Greene speak at the Melbourne Convention Centre. There was one group, but several other members went individually under their own steam as well to that. So it was more members than we actually saw on the night actually went there. 7th of April, we had 62 public here. Unfortunately, the clouds weren't very favourable, so I suspect we'll get a few of them come back at the May public viewing night. Unfortunately, those clouds, I suspect, kept a few people away. Trevor gave a talk actually on eclipses, and we're hoping when he comes back from Exmouth that he's going to be able to put together another talk on his experience with this eclipse as well at one of these meetings, probably the May members meeting, all being well. Coming up soon, I believe Friday and Saturday, there's this thing down at Bruthen. with the ASV, the LVAS, and I couldn't remember if it was Tourism Victoria or one of the other tourism places. So it's a Gippsland Tourism Authority. Not a Victorian, okay, yep. We don't need any help with telescopes or anything like that because we have enough members that are going down there, given that this is a very long distance one as well and several societies involved. So we don't need any extra assistance from that at all. Working Bee is this Saturday, as usual, beginning at 4 o'clock, but the cosmology group will also be here at about 6 o'clock for a talk. So Eden will give a talk on cosmology at the same time that evening. But hopefully by 6 o'clock, any noise from the Working Bee has started to subside, and you've got the barbecue on at that time. Committee meeting is next Wednesday. Then in May, we're pretty solidly on in the first week for viewing nights for schools. We've got Mornington Primary, we've got Year 3-4 here at the Briars, St Augustine's Primary out at Camp Mannion, and Mornington Primary, a second group of them a couple of days later. So it's going to be a big week that week before Guido does a talk at the public viewing night. So that week is going to be pretty full on for seeing school kids and talking to them. Cosmology group will be meeting on the 13th of May here at the Briars, which is a Saturday, and our next monthly meeting is showing there. Now, looking further ahead to the 6th of July, there's Neil deGrasse Tyson, who's also going to be at the Melbourne Convention Centre, and I believe we've got one spare ticket left if anyone is interested in going. If you are interested in going, the cost is $150 for a B reserve ticket, and see either Nerida, Jamie and Dave, and they'll now put their hand up in the air. So if you want to see who they are, there we are. If you're interested in a ticket, there's one left. See them sometime tonight. And now on to our good VP for Sky for the month.
For April 2023, so year is getting along fairly rapidly. A couple of things to watch for in April, May. There's a few exciting things. Full moon actually occurs on the 6th of May, and new moon, which is also actually it's not, sorry, is the 20th of 4th. That would be the moon that is the eclipse. Now I'll talk a little bit more about the eclipse later on. Looking at the various things that may interest people, comet linear, 0.2 degrees northwest of Rho Sagittarius, 3 a.m. Now a lot of these things I'm presenting tonight are actually very early morning objects, so not for the faint-hearted or those who like their bed, especially in the cold winter. Pan-star, 1.3 northeast of Eta Aquarius, and on the 20th of the 4th, which is tomorrow, say it again, tomorrow, you've got the hybrid solar eclipse. Now, I did actually read up on what a hybrid solar eclipse meant. So apparently it starts off as a partial, then becomes a full, and then goes back to a partial. So apparently they're very rare. Out of 241 total eclipses, there's only been about 7 hybrids. So if you actually want to see this totality, you better find a very quick way of getting to either Exmouth or somewhere out in the Indian Ocean. Now we have 2 members, one out on the Indian Ocean, Trevor Hand, and another one probably be standing room only at Exmouth, along with half the world's astronomers. So that occurs tomorrow around about 2 p.m. I'll give you more accurate times a little bit later on with respect to the eclipse. The Lyrids meteor shower occurring between the 16th and the 25th of this month, so it's in progress now. Its maximum is on the 22nd, so in a couple of nights' time. So for those who want to see meteor shower, opportunity to go out there is a couple. There's actually 2 going at the moment, along with a.
What's the weather forecast for tomorrow? You know?
Oh, I'm doing the astronomy stuff, not the weather. Okay, Comet Wild is in Sagittarius. When we get the next slide up, I'll show you how to find Sagittarius. Quite easy. Mercury's in inferior conjunction on the 2nd to the 5th. Basically means it's between us and the Sun. Unfortunately not in a good spot to give us a transit, so we miss out there. And on the 6th of the 5th, we have a penumbral lunar eclipse. And I'll do a little bit more about that later on and even explain what a penumbral eclipse is. And Uranus is in conjunction with the Sun on the 10th of the 5th. So what you can start gathering from this is all the big planets are pretty well in the same part of the sky, and you're either not going to be able to see them or you're going to be getting up in the morning to see them. So the April-May night sky looking south. So we have the south celestial pole there, and this is the ecliptic plane, which, because we're getting into winter, gets a little bit higher in the sky. It's just a function of the actual tilt of the Earth. I won't go into full explanation. Sagittarius, which I spoke of earlier, you can find it by, what they call this little teapot. And if you look up there, it's quite obvious to find it, right next to the tail of Scorpio, which is another easy one to find. They've both got quite bright stars. And for anyone wanting to look at the night sky, particularly over winter, Scorpio is probably a good spot to start, or a good constellation to start. Tarantula Nebula and 47 Tucana are getting a little bit low, especially here at the Briars. You're not really going to be able to see much of them. And but Eta Carina is quite high, along with Omega Centauri. And another one I'll point out, which is probably better on the next slide, is Virgo up here. And when Chris gets up and does his Astro Mo Pho, it'll be a good, you'll understand why being able to find Virgo might be helpful. Okay, so looking to the north, I just need to, hang on, did that go forward, did it? Whoops, okay, mucked up there. I'll put the two south skies up. Okay, so Virgo is up there, it's on the ecliptic plane, and there happens to be a whole heap of galaxies in Virgo, so just keep that in mind. The planets, Mercury is currently in the evening sky, but due to the vagaries of its angle in relation to the ecliptic plane and Earth and that sort of stuff, it's actually very low on the western horizon and probably not the most visible due to its proximity to that horizon. It's past its maximum elongation and it's on its way to inferior conjunction. And it pays to keep in mind Mercury covers a quarter of its orbit every 22 days, so rather rapid little mover. Venus, very bright in the western evening sky, moving from Aries into Taurus. It passed the Pleiades a few nights ago. It's not one you're going to have any trouble finding. If you go out there and there's no cloud, it's a big bright star out in the west there. It's probably the most obvious thing out there. Earth and Moon are aligned with the Sun this month, which is causing the total solar eclipse. It basically means because the Moon is inclined at 5 degrees to the ecliptic plane, it doesn't always pass directly between the Sun and the Earth. So the only time you're going to get a total eclipse is when it's passing through its orbit as it passes through the ecliptic plane, known as the ascending and descending nodes. So it's actually in that descending or ascending node at the moment. I'm not sure which one it is, but it's putting it in the right place to run a solar eclipse. The eclipse is on the 20th. 2 p.m. is the mid-time of the eclipse. I'll give you the start and finish times a little bit later. Well, actually I'll put it there, about noon to 3 p.m, although they're a little bit out because I think I did them to Western Standard Time. You will need to be in Western Australia to see anything decent of it. Exmouth to see totality, and Western Australia will see a fairly big chunk of it taken, and Victoria we're going to see about 11%. Mars is in Gemini in the early evening western sky. It's starting to get a little bit far away now for anyone who wants to see any detail on it, unless you have access to an extremely big telescope. Don't worry about it, it will be back in 2 years' time. And that's just a vagary of its orbit and ours. Jupiter was in conjunction on the 12th of the 4th, meaning it was the other side of the Sun. And the interesting thing now is if you're at Exmouth and you want to watch the total eclipse, you'll actually get to see Jupiter. It's about 6 degrees from the Sun. So once the Sun's blotted out, you should be able to see the planet. Okay, now you all wish you went, don't you? Okay, Saturn can be found in Aquarius in the eastern sky. that is the morning sky, AM. Fairly low to the horizon now. It will slowly rise as it eventually moves back to our evening sky. It's quite bright compared to the constellation stars that are around it. So it should be fairly easy to pick up for those who are keen to get up early in the morning and have a look at it. Uranus is currently lost in the western evening twilight. Too low, it's still in a fairly light patch. It's hard enough to see as it is at the best of times. And it's moving towards its conjunction in May. And Neptune has passed its conjunction, so it's gone around the other side of the sun and is in the eastern sky in Pisces. So if you want to see any of the 4 big planets, be an early riser. So the appearance of the planets, in comparison, you can see Venus is quite large at the moment. It is getting or heading towards what's known as maximum elongation, and as it does that, it actually gets closest to us, so the disk actually enlarges. Mars, on the other hand, we've actually sped past Mars and getting further away from it in our orbit because we're faster, and so it's really just a little red dot now. You can still pick it up, but don't expect to see much more than a red dot. Saturn, for those who do get up in the morning, you will still see the rings, but you'll notice now the rings are starting to close. And that's because in 2 years' time, we will pass through the ring plane and all you'll see is the planet. So basically that means the planet will be side on, the sun will be here, and we'll go through that and the rings, and then as we go, they'll start to open the other way. So if we watch Saturn as it goes, it tends to do that over a 30-year period, for those who can be bothered watching it for 30 years. Jupiter, always fairly specky, no matter when you look at it. Can't really see it at the moment, unless you want to go to Exmouth and look at it during the total eclipse. And Uranus and Neptune, pretty much in the same boat. They're all very much in the vicinity of the sun at the moment, which makes them pretty useless for observing. The other stuff, a couple of comets, there's a few more than that. I didn't bother with the other ones. ZTF, which we've been talking about the last couple of months, is about 13th magnitude now, so kind of getting to the limits of your vision. And I think for those of us who had a look at it in the last few months, we weren't all that impressed. So it's going to be even less impressive now. Pan-STARRS K2 is in Eridanus, the river, at about 10th magnitude. On the 13th of the 4th, it was very near to a spiral galaxy, NGC 1532, in Eridanus. And I've only put that there, I know we're past it, but over the course of the month, it actually follows the river. So if you really want to try and spot it, it heads up the river, okay, without a paddle. All right, Pan-STARRS K1 is in Indus, which is very close to the South Celestial Pole, or down that area. Rises about 90 minutes after twilight, and it's currently about 11th magnitude. The thing you'll notice with most of these comets are all around about 9th to 11th, 12th magnitude, so do need a telescope to see them. Comet Wild moved into Sagittarius, about 11th magnitude, riding in the evening southeastern sky. So it's obviously coming up right behind Scorpio, which is rising, I think, about 10 o'clock at the moment. So it's going to be just behind that. Good luck spotting it. Sagittarius is where the galactic centre is, so there's a lot of light and a lot of objects in that part of the sky. And Comet Linear currently also in Sagittarius, so maybe have a look and see if you can pick out which one's which. There's a couple of meteor showers, the Gamma Normids, active between the 25th of the 2nd and the 28th of the 3rd. What? What month are we in? We're in April, aren't we? That should be the 4th. My mistake. Not a high rate, about 6 hours per max, generally bright white, yellow and orange, and the Pi Puppets. That's the wrong one. All right, and the Pi Puppets are a young southern shower, best between 15th to 28th, with a maximum of 24th of this month. Righto, the eclipses, partial solar eclipse. We call it a partial here because that's all we're going to see. Be about 11% of the sun. We'll have a little chunk bitten out of it. And starting at 11:15 p.m. and ending at 3:01 on the dot. All right? If you get there at 3:02, you're going to miss it. All right. The maximum chunk's probably taken out around about 2 p.m. So if you're not keen on standing there watching it the whole time, if you get to it about 2 p.m. and get your super duper sunglasses out, you should be able to see a nice chunk out of it. Another one occurring before the next meeting is a penumbral lunar eclipse on the 6th of May. It actually did say the 5th, but it doesn't start until Eastern Standard Time until 1:12 a.m, so it's actually the 6th. Alrighty. Essentially the Earth casts a shadow out into space. One of them is called the umbra, which is where its deepest shadow is cast, and that's a little point behind it. It also casts another lighter shadow called the penumbra, and the moon passes through that penumbra. So you won't get a blood moon out of this. You won't get a total lunar eclipse. What you'll get is you'll get a slight dimming of the moon, which may be interesting in that all the last ones we've seen have all been total eclipses. So the only downside, it starts at 1:12 a.m. and ends at 5:34 a.m. So one to leave your cameras out overnight, I think. Alrighty. Upcoming events. I'll just provide another warning, member subs for 2023. The renewal link will be closing very shortly. For those who intend to renew, get your renewal done, or you'll have to pay a $30 rejoining fee. Saturday, 22nd of April, starting at 4 p.m, we've got the working bee and the barbecue, general tidy up, etc. And did I see that Eden's doing his Cosmo talk? Okay, so that's a little bit extra bonus. First week of May, we've got a huge number. Peter did actually put them up there. We've got the 1st, 2nd, 3rd and the PVN on the 5th. For anyone wanting to attend the first three, you will need a current Working with Children check. And if you want to refer to Peter's email, dated the 17th of April, he'll actually give you the details of where and when for those upcoming events. Science information provided by Astronomy 2023 by Wallace Dawes and Northfield. Any questions? Oh, Phil, I thought I got away with it. What have you got, mate?
What's the river?
Oh, the river Eridanus. Now, it might be... I've done some real serious cut and paste issues. I can never find them from here.
What's the name of it again?
It's Eridanus, or Can someone see it? Because it normally comes out of the south, I thought, so... Yeah, unfortunately I haven't put the, that's not the north one. That's, yeah, I've done the south twice. So, Hydra. You haven't got a go-to scope, have you? You haven't got a go-to scope. That's why I gave the spiral galaxy. Yeah, so, yeah, and it will be above that along the river. It's travelling up the river the whole month. Okay. Thank you.
Okay, thanks everyone for coming tonight, and we'll get started with Astro Mo Pho. which is our monthly astronomical photo challenge for members. Okay, this month's challenge was to photograph objects in the Carina constellation. So Carina is pretty easy to find. We've got the pointers. Was there a laser pointer here? Yeah. So we've got the. There we go. No. That way. Okay, so we've got the pointers there, Southern Cross over here, and then Carina comes out and across from the Southern Cross all the way out to Canopus over there. Carina is part of a larger asterism called the Argo, the Argo Navis, which is the mythical ship that Jason set sail in when on his quest to find the Golden Fleece, and it's made up of Vela, the sails, Carina, the hull, and Pupus, the stern or poop deck. So poop deck is where you go to do the obvious. And it's at the back of the ship because you don't want poop on the front of your ship. So there you go. Canopus is also the second brightest star in the sky, so pretty easy to find out there. We had quite a few entries this week, so no time for hamsters. The first one that we've got is a time-lapse sent in by Dave Rolfe down at the Tooradin Lookout on the 25th of March when they were out trying to photograph some aurora. And you can see here again from the previous one, we've got the Southern Cross, the pointers and the Southern Cross here, and we've got Carina constellation going through there. So we've got the Carina Nebula here, Canopus there, and the constellations stretching through there. Got the Southern Pleiades here, the Gem Cluster, and I think that's the Beehive in there. So we just play that through. That's basically the way we see it moving through the course of the night, and we've got some nice aurora going on down there as well. Next one we've got is an image sent in by Chris Black, last minute entry of a nice wide field view of the Carina Nebula. So we've got the Gem Cluster up there and the Carina Nebula through here, the Gabriel Mistral Nebula up there. This was taken with Chris's Canon 6D DSLR, which has got a pretty wide focal, pretty short focal length, wide field of view of about 250 mil. So it gives us a nice view of the whole nebula as we can see it through there. Next we've got a couple of images by Dave again with his 130 mil refractor. We've got the what we've got NGC 2516, the Southern Beehive, which is down in the bottom there. That's a monochrome image, and the Whirling Dervish. Is that what it's called? Whirling Dervish Nebula, up in the top right, taken in what was it? HA03 and S2 filters in the top right. We've also got this one here of the Whirling Dervish by Guido Tack as well. And if you're wondering how big the Whirling Dervish is, we've got a banana for scale down the bottom. So that's the Banana Nebula down there, which Guido's also included in his photo, taken with his William Optics Zenithstar 73. 9300 second images processed in PixInsight with dynamic narrowband combinations, which means basically it's a way of combining the different monochrome images into different combinations of red, green and blue to give different colours and details in the nebula. We've also got this one here by Nick Axaris, which is the Statue of Liberty Nebula. Also, it's near, close to the Southern Cross as well, near between the Southern Cross and the Carina Nebula, with his TS Optics 130mm refractor, L Extreme filter, which is a dual band filter, and his 294MC astronomical camera. So Nick's taken this in two different focal lengths of 910mm and 683mm, so one with and one without the reducer, to be able to pull out more detail in the nebula itself. So it's an interesting technique and image there. He's used the Leucomaticos pixel math, which is again similar to the previous image that Guido did, a way of combining the monochrome images to create different colours in the final image. And here we've got Nick's Eta Carina Nebula as well. So a couple of great images there. Next we've got a couple of images from Russell Smith, NGC 3372, the Eta Carina Nebula, and also the Statue of Liberty Nebula, taken with a bit of a different process. So Statue of Liberty is in hydrogen alpha luminance and LRGB, so it's a monochrome camera, and red, green and blue filters with a hydrogen alpha as well, and that really shows up all the red hydrogen alpha glowing around that nebula there as well. So nice image there. And the monochrome image up in the top right is just hydrogen alpha, so that's a narrowband filter just picking up the hydrogen alpha light from the Carina Nebula. And we've got this one here by Stephen Gilmore as well. With his Takahashi, no, that's with his Stellaire RH200 telescope. And that's a starless version of the Eta Carina Nebula there. So he's used a process to be able to remove all the stars from the photo and just process the nebula on there. These are a couple by me. Again, the Eta Carina Nebula and the Statue of Liberty Nebula with my 80mm refractor. Again, with these are also taken with an Optolong L Extreme dual band filter, so it brings out the hydrogen alpha and the O3 emissions, and my Astro camera. And these are just processed two different ways, and we see just two different color palettes coming through on the two different objects. Now these are both full frame, so they're not really cropped very much at all, so that is a pretty accurate size comparison of the two objects. So you've got the Eta Carina Nebula, which is around about 300 light years across. The Statue of Liberty Nebula in there is around about 100 light years across. Now, the other thing that I'll note is what up here we've got the Gabriela Mistral Nebula, and it was actually one of the first images photographed by the James Webb Space Telescope. So if we have a look at the zoom in on the Gabriela Mistral, we've got that feature there, which is this feature here on the James Webb Space Telescope. So it really gives us an idea of the power of my telescope, the power of the James Webb compared to what we see from a small telescope here on Earth anyway. Now we've got here a lot of areas in this image showing a lot of rapid star formation, and the shape of this feature here, which is the cosmic cliffs, is what it's called, is formed by the radiation from all the new hot white stars that have been created within the bubble there. And finally, we've got a first image here by Nikhil Joshi, which is, we can actually see the Keyhole Nebula in Eta Carina. So this is Nikhil's first image that he sent into us, so well done, Nikhil. And it's with his Celestron C8, which has got a pretty long focal length of just over 2 meters. And which he's able to give us, compared to the first image which we saw, which was a fairly zoomed out one, this one's fairly zoomed in, showing a tight view of the internal part of the nebula, and this dark patch through there is what's actually called the Keyhole Nebula. So this is the Eta Carina is just in there. That's the bright star down the bottom there, and yeah, it's taken with Nikhil's DSLR. So a great image there. So this challenge was completed by Nikhil Joshi, Guido Tak, Dave Rolfe, Russell Smith, Nick Exaris, Stephen Gilmore, myself and Chris Black. So well done to all of us. Now, next image. Next challenge, we've got a couple of things. We're looking at photographing our nearest objects and the farthest objects. So we've got the lunar eclipse happening tomorrow. As was mentioned, we've got a couple of members up around the area who'll be able to take some photos of the total eclipse. Fingers crossed for good weather. But from Melbourne, we've got a couple of, oh, hang on, well, before we do that, apart from the total lunar eclipse, we're also photographing distant galaxies as well. So Russell Smith suggested that we have a look at galaxies. We've got the Virgo cluster and the Leo galaxies pretty nice and high up in the sky, so they're in good positions to photograph over the next month. Looking south, we've also got, what do we got? We've got not Omega Centaurus? Centaurus A, yes. And a couple of others. We've got the Sombrero, what else? Southern Pinwheels in a good viewing position and that sort of thing. So a couple of good objects to be able to photograph over the next month. In terms of galaxies, you'll need focal length or Barlows to try and get them, or maybe come and use the bigger scopes here at the club. In terms of the solar eclipse from Melbourne, we're not going to get a full eclipse. This is roughly the view of the eclipse that we'll be able to get through a solar telescope or a telescope with a filter. The moon will start getting eclipsed by around about 1 o'clock in the afternoon, moving on to around about 2 o'clock. 2 o'clock we've got the most coverage, and then finishing up just at around about 3 o'clock. So these images are taken from Stellarium screenshots, and it just shows the progression of the moon across the sun as we'd expect to see it. So the usual warnings apply. Don't look at the sun. Don't point your telescope at the sun unless you've got proper filters. And even a digital camera pointed at the sun, if you do that without protection for the camera, you'll probably kill your camera. So just make sure you're using proper equipment if you're going to be doing that. There's no, I think you might have a bit of trouble sending a melted sensor in for a warranty repair. The sun? It's close to midday, Fred, so it'll be pretty high up in the sky when it's happening. It'll be coming from above. I'm not a weatherman either. Oh. Okay, so they're the usual avenues for submitting photos. The MPAS Facebook page, eScorpius members chat, or email them to me. Thank you very much for that. And then we've got our member survey. Recently we did a member survey which ran from the end of last year through to around about February, March of this year, where we collected a bit of information and asked a few questions of our members about what they thought we're doing well and what they thought we're doing not so well. We had about 30 members respond to the survey, and we got some pretty interesting feedback from them. One of the first questions was your reasons for becoming a member, and as expected, most of us were joined up because we have an interest in, particular interest in astronomy. But interests in general science and knowledge sharing were also pretty popular reasons. 4 people had other motives for joining. I'm not sure what they are, but maybe some of them thought we were an astrology cult, but not the case. We've got a pretty good spread of topics of interest there from members. The most popular one, as you can see, is planets, the solar system, closely followed by galaxies and nebulas and star-forming regions, the main areas of interest. Alien life and UFOs, not so popular. Exoplanets, not so popular, although there is a lot of work being done in exoplanet research and that sort of thing, especially with the new telescopes up there, so could be a growing area of interest for a lot of amateur astronomers. Other areas of interest included quantum physics and visual astronomy, so I don't know who conducted a survey from an astronomical society without asking about visual astronomy. Meeting attendance. One of the things we wanted to know was basically how many of you are coming, why you're coming, and why you're not coming to the meetings. So around about 35% of members, or not members, I should say people who responded, attend the meetings frequently or occasionally. Online viewing of the recorded meetings is fairly high, so a lot of people like to view the meetings on YouTube, which isn't actually reflected by the responses on the survey. We only had 2 responses saying that they view the meetings online, but figures show that actually it's a bit higher than that. So, other reasons for not being able to come to meetings included transport difficulties. Either people find it difficult driving at night, or they can't drive at all. COVID was another one of the other reasons, because well, the past few years, COVID, well, we weren't having meetings, and apart from that, it was also difficult for people to get here when we were, and also just made it a little bit scary for people to come out. Distance was another one, a few people living a little far away, and someone was honest enough to say they're too lazy to come. So some of the feedback that we got was to make the meetings a bit shorter, but we all know we can just come and stay as long as we like. We're not locked in, the doors are open. Putting them on Zoom, which is a difficulty because we don't have enough bandwidth up here to be able to live stream the meetings, so putting them on Zoom is a little bit difficult. Other feedback was to maybe have the meetings earlier, because it gets a bit late for some people, and other people wanted them a bit later because they can't get here in time after work. So a bit of everything there. Barbecue attendance was the next one, and we had around about 32 people attend the barbecues frequently or occasionally. The main reason people can't come to the barbecues is because they have other commitments, be it social, family commitments, or other things coming up. Again, difficulty driving and getting here. COVID was another reason recently why people weren't coming to the barbecues, and someone also said they hate sausages. So don't know what we can do about that. We do try to provide other food as well. Extracurricular stuff. So we had some pretty good responses on this one. About 66% were interested in joining discussion groups like the cosmology group. So we might look to try and get some more interest groups happening, although they do need people to run them. So if anyone is willing to put in the time to help organise a interest group, as Eden White does, then please contact the committee. 83% are interested in field trips, star parties and other events, and we have been organising quite a few, such as the Brian Cox and the Brian Green events. There's the South Pacific Star Party, which has been organised for attending through the club as well, although that's closed it's closed off now. Snake Valley was another one that happened, so just keep an ear out for those, and as they come up, and if you're interested, then yeah, by all means they're available for members to join in as well. And 66% were also interested in assisting at PVNs and school nights, and we have seen a lot of members coming up to the PVNs lately and helping out, and just getting used to the flow of things, how they happen around the PVN, and being able to help, learning to be able to help on the scopes and on the equipment during those. So as Mark said earlier as well, if you doing the PVNs is okay. If you do want to help out on the school nights, though, you do need a Working with Children's check, which is freely available for volunteers. And yeah, that was it. That was some good feedback on the survey. So basically, people were pretty happy with the club. We got a lot of good feedback. People appreciating the work that we do here and enjoying the club. And there'll be a full report on this in the next newsletter as well. So there we go. Any questions? No, very good. It means I did a good job.
Tonight's feature is going to be by this lady, Dr. Sabine Hossenfelder from the Frankfurt Institute of Advanced Studies. She's a quantum gravity fellow there and a theoretical physicist, and usually not shy at giving debunking talks online to strange things that she may hear. Now, this is a public lecture that was given at the Royal Institution in Albemarle Street, London, last year, and this is ahead of her book, and indeed our library actually has this book in it.
Well, thank you everybody for being here. When it became clear to me that I'd be talking on Friday evening at pop time while the tube is on strike, I thought I'd be standing here alone. I guess this is the most dedicated audience I'll ever get. Existential physics, yes. I gave a talk about this about 2 months ago at a literature festival, and they didn't like the title. So when I showed up and I looked at the program, I found that I'd be talking about the meaning of life. And I'm afraid it will not get quite as existential as that. But I thought I'd start with explaining what I'm even talking about. What is existential physics? What I mean by this is those aspects of physics that concern human existence. For example, the nature of time, what changes, the beginning of the universe, where do we come from, the structure of matter, what are we made of, constraints, limits, what can we do, and what can we know. Now, people who have known me for some while would find this quite a change of direction. I'm more known for talking about what we can't do. So if there are some headlines in the popular science news that proclaim that we can travel faster than the speed of light, or we can send information faster than the speed of light with the quantum internet that is soon to be coming, or that we can create negative mass, or make contact with parallel universes, then I'm the one who has to say, no, you can't do this, no, they didn't do it, no, they haven't done it. And I do think that this is kind of important, debunking headlines, but it's also, in the course of time, it's become a little bit depressing. And I found that it portrays a very one-sided picture of physics and also of me, so I wasn't quite happy with it. And I thought there's more to physics than that. Physics also tells us what is possible, and it opens our mind to new possibilities. And maybe that's a little bit surprising. It's not quite how we think of physics, that it tells us something about quite spiritual ideas, something about our own existence. But if one thinks about it a little bit more, I think maybe it's quite natural. So I've tried to draw on here science, philosophy, and religion with some fuzzy boundaries to make clear we are not really sure exactly where they end and where they begin. And the foundations of physics are kind of slightly overlapping with philosophy and religion, and the scientists who work on it are not always quite clear which side they are actually on. And I think what I mean with this will become clear in the duration of this talk. Okay, before I say anything else, I have to say that everything I'm going to say today is just for all we currently know. So when I was writing my book, I realized that I was constantly using this phrase, for all we currently know, this and this, for all we currently know, it's so-and-so. And then in the end, I just put it in the preface and said, everything I'm going to say should come with the phrase, for all we currently know ahead. And the same is true for this talk. So I want to start with the question, does the past still exist? This is a question which has been brought to our attention basically by Einstein's relativity. And there's a lot to say about relativity, but I'll try to make it fit into a 1-hour talk. There are 3 important ingredients that we need to know. One is that the speed of light is finite. It's very large, 300,000 kilometers per hour, but it is finite. It's the same for all observers, so it doesn't matter if you're running, which direction you're running. The speed of light is always the same, and nothing goes faster than light. And to be precise, the last 2 are only true for the speed of light in vacuum, but I'm a theoretical physicist, so we always do our thought experiments in vacuum. Now, this sounds kind of innocent at first, but if you think about it a little more, it has a perplexing consequence. If I ask you a very simple question, am I here now? Then the answer is, well, you can't tell, because by the time you see me, I'm already moved on to the future. So you always see me like I was a little bit in the past. Now, of course, this is a ridiculously tiny amount of time. You could go and measure the distance and calculate how long it took for the light to travel from me to you. and it would be a fraction of a nanosecond or something. So kind of not exactly what we would notice, but in principle, that's true. And as I said, the speed of light is a maximum speed. So it's true for all possible information that you can receive. Everything you see, everything you perceive it as it was a little bit in the past. Now you could say, well, but I do know what the speed of light is, so I can just calculate how long did it take for the light to get from me to you, and then I could say, well, when you actually said the word so-and-so, I was just scratching my head or something like this. So you could try to say, well, I can figure out which two moments belong together. So you could try to reconstruct a notion of now. But it turns out that this is not all that simple due to relativity. Now, maybe, you know, the normal person's reaction would be, oh my God, physicists. But as I say, I think just because you're here on a Friday evening listening to a public lecture on existential physics, I guess you're not quite the average person on the street. So I'll try to explain this in a little more detail, why relativity is weird and why it makes it so difficult to define a notion of now. So suppose you're standing on a hill or something and you're looking at a train that's going by from the left side to the right side, and your friend is in the train, standing exactly in the middle. And if the train hits a particular position where the red arrows are, there'll be light flashes triggered in the train. So they are the light flashes. And the question is, do you see them at the same time? Now, keep in mind that she's directly in the middle of the train. Those two light flashes are exactly at the same direction, at the same distance from her, and they are also at the same distance from you, and you know the speed of light is always the same. So if you want to figure out what will you see, well, you can just forget about the train, doesn't really matter, and the light arrives at you, and your conclusion is, well, they must have been emitted simultaneously if they arrive at me at the same time, because I know they have exactly the same distance. So far, so obvious. But now, what does your friend see when she's on the train? Well, so again, the light flashes, but now the train moves on, and she moves towards one of the light beams that's emitted from this flash and away from the other one. So it seems to you that clearly she sees one of those earlier than the other one, and she would say, well, they're not simultaneous. So two events that happen at the same time for you do not happen at the same time for her. And it might seem like this is just a quirk of your perception, you know, that comes from this weird arrangement or something, but it turns out in relativity, in Einstein's theory of special relativity and also in his theory of general relativity, that's a general feature. It's just impossible to construct a notion of now that does not depend on the observer. This notion of now elsewhere always depends on where you are and how you travel. So it's a kind of a very personal thing, actually. And it has the consequence that your past may be somebody else's present, or the other way around. Your present may be somebody else's future. And the only logical conclusion that you can draw from this is that either nothing exists now. So this is one conclusion that you can arrive at. You can just deny that you can say anything about what exists at this moment elsewhere, or all moments exist the same way. And, well, I don't know about you, but I'm quite used to talking about things that happen elsewhere now. So I think that's just a natural sense in which we use the word now. And then we arrive at the conclusion that really all moments exist in the same way. It's called the block universe. It's a consequence of Einstein's theories, and it clashes with our intuitive perception of time. We perceive one moment as now, and we think it's a special moment, but according to Einstein's theories, all moments are equally special in that regard. So the block universe, it kind of just sits there. There's no particular moment singled out in it, which corresponds to this moment of now that we perceive, that comes from our particular position in that block universe. In the block universe, different times don't cease existing if you're not there, the same way that different places don't cease to exist if you're not there. Now, I asked, does the past still exist? According to this, the answer is yes. The past exists the same way as the present does. Why did I not ask about the future? Well, it's because quantum mechanics makes the story a little bit more complicated, and I'll say a little bit more about quantum mechanics in a moment. But yeah, so does the past still exist? For all we currently know, the answer is yes. And I know a lot of people find this surprising, but it's actually quite uncontroversial in physics. It's one of those things that we learn as students in the second year or something, and the first time we hear about it, we're like, oh, this can't possibly be true. But the mathematics is not all that complicated, and this has been thought through many times, and so yeah, for all we currently know, it's actually correct. So there's another way that we can look at this from a slightly different perspective that I want to talk about now. Can information be destroyed? So before I go on, I have to say that the way that we talk about information in the foundations of physics, at least in the areas that I work in, it doesn't mean a terrible lot. It just means it's all the details that you need to specify a system at one particular moment in time. We also call this an initial condition. In a classical system that you are used of, like for Newton's laws, throwing a stone or shooting an arrow, that kind of stuff, it would be the position and the initial velocity. That would be the entire information about the system. In more complicated systems, it's more complicated information. There are more numbers, but basically that's what it is. In other areas of physics, information means more than that, but this is the way that I'll use it today. So all fundamental laws we know in the foundations of physics work in a particular way. They work by using differential equations, and it sounds a little bit complicated, but really the only thing that it means is that we specify all this information about the state of a system at one particular time, and then we use this equation to calculate what happens later, or we could also calculate what happened earlier. Indeed, this equation, which we call an evolution law, just connects two different times, and it's a one-on-one map. So if I give you the information, the entire information of a system at any one time, you can calculate what happens at any other time, both forward and backward in time. In principle, this time evolution is reversible. You can do it forward and backwards in time. Which means that this information is just reconfigured. It's never destroyed. So it doesn't really seem to match with our experience, again, because it's certainly the case that the information can get so badly scrambled that we can't use it for anything. So, for example, if you take a book and you burn the book, so in principle, for all we know about the fundamental laws of nature, the information about the book cannot be destroyed. It's still there. It's there in the ashes and in the smoke and in the tiny correlations between them, and they spread out through the room. That, of course, means that for us, it's completely useless, this information. But according to our equations, it's still there. Okay, so this is all fundamental laws we know, except there are two issues. One is the measurement in quantum mechanics, and then there's black hole evaporation. And I'll talk about those in a little bit more detail. So in quantum mechanics, we also have this fundamental law, which is a one-on-one map from one state to another state, and that's called the Schrödinger equation. The Schrödinger equation tells us how the wave function changes, and the wave function is the thing that we use in quantum mechanics to describe everything. Literally, there's a wave function for anything. It could be an individual particle, like an electron, or it could be a molecule, or it could be a cat, so that there are wave functions for everything. The wave function is just a device to calculate probabilities. So that's the peculiar thing about quantum mechanics, is that we can't actually directly observe the wave function. We can only observe the probabilities of getting a particular outcome. And I've tried to illustrate one of the consequences with this little figure. So the wave function could tell you that you have a particle which has a 60% probability of being in one place and a 40% probability of being in another place. But now when you measure the particle, you know where it is. So you have to update the wave function for being 100% wherever you have measured it and zero in all the other places. Now the issue with this is that there could have been many different wave functions that could give you the same result. It could have been this particular wave function with 60 here and 40 there, and then it would have been a fairly likely outcome to measure it on the left peak, or it could have been the other way around, and you were just particularly lucky to see the particle in a place where it was unlikely to be, but still you saw it there. And what this means is that this process is not reversible. If you know what the outcome of the measurement is, you cannot find out what the initial state was. You don't know what the wave function was. So measurements in quantum mechanics, the way that we use them at the moment, just in the mathematics, are not reversible. So they break this idea that information survives. But do they really describe what happens? So that's a big open question. It's called the measurement problem in quantum mechanics. A lot of people, including me, don't actually think that the measurement update is fundamentally the correct process. It might only be an approximation to a yet-to-be-found better underlying theory, in particular because it brings up some inconvenient questions like, who measures the universe? If you want to make a theory for the entire universe, you write down the wave function for the whole universe. Well, who measures this? It doesn't really make any sense. So the way that we're using the theory right now, it seems to be missing something. So what's with black holes? Well, at first sight, it seems if you have a black hole and you throw something in, and there could be a book or something else, then the information just gets lost behind the horizon. And you could say, well, okay, but it's just sitting there behind the horizon. Just because I can't retrieve it doesn't mean it's actually been destroyed. It might still be there for all we know. And that was the situation before Stephen Hawking. And then Stephen Hawking came and said, well, but actually the black holes don't continue to sit there. Instead, they evaporate, they emit quantum radiation. And the issue with this radiation is that it's basically random. It doesn't contain any information other than the mass of the black hole and the electric charge and the angular momentum. So the radiation does contain 3 bits, if you want to put it this way, but that's not very much, in particular not an entire book. So to give you a sketch of this problem, suppose you have some initial black hole and you throw a book in, or a turkey or apples or whatever have you, and you create a slightly bigger black hole. In all of those cases, we assume it has the same mass. Then the thing evaporates and you're left with this random radiation. And again, you have the same problem as with the measurement process. If the only thing you have is this random radiation, then you can tell, well, what the mass of the black hole was, but you have lost all the information about what was inside the book, or the name of the turkey or what have you. So black hole evaporation, again, seems fundamentally irreversible, as opposed to things that are apparently irreversible to us, like burning a book. So at least in our mathematics, black hole evaporation seems to work entirely differently. And this is what gives rise to the black hole information loss paradox, which you've probably heard about. Black hole evaporation is inconsistent with quantum mechanics, because quantum mechanics, before you're making a measurement, is time reversible. But a black hole, even without making a measurement, breaks this time reversibility. So it just mathematically, it doesn't fit together. It's an actual inconsistency in the theory. Most physicists believe that something is missing in Hawking's calculation and that the process is actually reversible. that is quite plausible because we don't have a theory to describe the quantum behavior of space and time itself. So that's called a theory of quantum gravity. Since we don't have this theory, it's not included in the calculation. So quite possibly that's it. The problem is the astrophysical black holes that we have experimental evidence for, that we see out there in the cosmos, they have an extremely low temperature of this radiation. It takes hundreds of billions of years for them to evaporate. Actually, at the moment, they wouldn't evaporate at all because even the cosmic microwave background is hotter than the temperature of those black holes. So it takes a really, really long time for a black hole to evaporate, and so we can't experimentally test what's actually going on. So really, we don't know. So what's the conclusion about the question, can information get destroyed? Depends on what you believe happens in a measurement and in black hole evaporation. I think the answer is no, but I don't want to talk too much about my own opinion. If you want to know, you can ask me later. So since we were already talking about astrophysical things, let's talk about the entire universe. How did that begin? So that's a question which sits very much on this overlap between science and religion and philosophy. How did the universe begin? Was it especially made for us? Does it need a creator? Are those questions to which we can never find the answer, and so on. And the foundations of physics sit right in this entire mess, so to speak. So how does modern cosmology work? Yeah, there's Einstein again. Modern cosmology is based on Einstein's theory of general relativity, which says that gravity is really an effect of the curvature of space-time. And this theory tells us that the universe expands because there's matter in it. The rate of the expansion is determined by the amount of matter and energy in the universe. So it's a little bit different depending on if there's more radiation or more matter, if you have dark energy, and so on. And from measuring the rate of expansion, we can figure out, roughly speaking, to make a long story short, what's in the universe. And this theory, or this particular model for cosmology, which is called sometimes called the concordance model, or sometimes called lambda CDM. Some people call it the standard model of cosmology. It's made a lot of correct predictions. It makes predictions for the formation of structures, like how quickly the structures form and how they're distributed. It predicted the cosmic microwave background and also the properties, the abundance of light atoms, redshift of distant galaxies, and so on. So it's a good theory. Let me put it this way. But it has a peculiar property, which is if we take those equations and we extrapolate them back in time, then at some point the energy density in the universe becomes infinitely large, which doesn't really make a lot of sense. It just creates a singularity. It's not just the energy density of matter that becomes infinitely large, also the curvature of space itself becomes infinitely large. And what does that mean? It doesn't really seem like something that could possibly be physically real. Indeed, a lot of pretty much no physicists I know thinks that this is actually what happened. More likely, it just indicates that the equations break down. So now what? Well, one of the reasons those equations probably break down is what I already said earlier. We don't have a theory for the quantum properties of space and time, which should become important somewhere when the energy density gets very large. So basically the answer is we don't know. But as you probably know, physicists have put forward a lot of different theories for how the universe begins. So how did this come about? Well, remember how natural laws work. We just talked about this some minutes ago. If you have a final state in an evolution law, you can roll this back in time to an initial state. And now if you take this initial state and you roll it forward with the same evolution law, you get the correct final state that agrees with your observations. And you can always do this. If you have an evolution law, you can always create an initial state. So at first sight, it seems a little bit perplexing. How can we ever figure out what's the right evolution law if we can just fumble together an initial state that will work together with it and give us what we observe? Now, if we do this in our everyday life, shooting your arrow or throwing a stone, then you can test these situations by choosing a different initial state. You could shoot your arrow in a different direction, from a different position, or you could take a movie and look at where it is at any moment of time and extract the evolution law from this. But we can't do this for the entire universe. There's only one initial state, and we can't take a movie of 13 billion years. So that doesn't work. So how do you ever know what's the right law for the universe? Well, the way that we do this in cosmology is that we take the law which is the simplest, and that's the concordance model that I just talked about. But if you are willing to leave aside this requirement of simplicity, you can change the evolution law back in time, and this gives rise to all kinds of different stories for the beginning of the universe, and those are the stories that you've probably heard about. So since we don't have evidence for what happened at those high energies in the early universe, it's possible to change the equations. Usually the way that this works is that you choose an equation which looks very similar to the one that we have in Einstein's theory up to some time very early in the universe where safely no one has any good data, and then before this you can change the equation whatever way you like, basically. And this gives rise to all kinds of different explanations. Instead of a big bang, you could have a big bounce. So this happens if you have an earlier phase of the universe which contracts, and then it doesn't run into a singularity, but it reaches a smallest size, and then it starts to expand again. This is called a bounce. Those bounces could repeat, in which case you get a cyclic universe. You could start with a phase that is neither space nor time. This is called the no boundary proposal, and was proposed by Hartle and Hawking. You could start from a black hole, and there could be a 5-dimensional black hole. It could be a gas of strings, or it could actually, I have those mixed up. Okay, yeah, sorry. I've confused myself over what I wrote there. It could be something that has neither space nor time, like a network of sort. This is something which people have also proposed. So you just have a network of points, and our notion of space, which emerges at a later time, comes about if the network sheds a lot of connections, so it resembles kind of a smooth lattice, basically. So what's the problem with all those? Well, a good scientific explanation must be simpler than the observation it's trying to explain, and it should be as simple as possible. Unnecessary assumptions are not allowed. And this is the problem with all those stories about the early universe. They make a simple story more complicated. So the simple story that we have is the standard model of cosmology, which, if we roll it back in time, gives us the Big Bang. We think that this is probably wrong, so we don't know how the universe began. And this is, for what science is concerned, is really the only thing we can reliably say. So what's with those other theories for the beginning of the universe? Well, they're mostly not wrong, but we can't tell that they're right either. So we just can't apply the scientific method to pick any one of them. They all fit to our observations, at least so far. So the way that I like to think about them is that they're basically modern creation myths written in the language of mathematics. And you can believe whichever one you like. My friend and colleague Tim Palmer has called those ascientific, and I think it's a good term. It's not that they are somehow unscientific, that it'd be going too far, but science doesn't say anything about whether they are right or wrong. So how did the universe begin? We don't know, and we may never know. Okay, speaking about universes, let's talk about some more universes. In particular, I want to talk about the multiverse and the question whether copies of us exist. You've probably heard of the multiverse, so it's this idea that our universe isn't the only one, but there are many, many other universes out there, possibly infinitely many of them. And there are multiple multiverses, so to speak. Brian Greene has written a book in which he lists 9 of them. I don't want to go through all of them, but I want to briefly remind you of the most widely known ones, so to speak. One is eternal inflation, which has it that our universe was created from a quantum fluctuation of some kind of field. This field is called the inflaton field. It doesn't really matter if you don't exactly know how this works. The relevant point is just that there isn't only one of those quantum fluctuations, but there are many of those quantum fluctuations, and they continue to happen all the time. So there isn't just one universe that's created from this inflaton field. There are actually infinitely many. So there are infinitely many Big Bangs, each give rise to their own universe, and there are more of them as we speak. Possibly the constants of nature in those other universes are not exactly the same as they are in our universe. So they could be very different. Some of them might be hospitable to life. Others might not be hospitable to life. What's the problem with this? Well, the issue is that those other universes are entirely disconnected from us. There are no observations that we can make that could refute or confirm that they exist. And it's not just that we can't see them, like we can't look at them, or it's something specific about light. There's no observation that we can make that could tell us whether they actually exist. There are other versions of the multiverse. For example, if our solar system and our planet and us, we grew out of such a quantum fluctuation in the early universe, and then in this matter distribution there were smaller fluctuations that gave rise to planets, galaxies, and so on and so forth. If this happens infinitely many times, then our planet and everyone and everything on it should repeat with small variations. So there are copies of us somewhere out there. Again, the issue is that we cannot possibly measure those. So they're out of causal contact with us. We cannot figure out whether they actually exist. There's no observation that can refute or confirm that they are actually out there. And to name one third example of the multiverse is the many-worlds interpretation of quantum mechanics. So as I said earlier, the way that we typically think about a measurement in quantum mechanics is that the moment you observe something, you update the wave function. It's also sometimes called the reduction of the wave function or the collapse of the wave function, so it's all the same thing. Strictly speaking, this is only one particular interpretation of quantum mechanics, and the many-worlds interpretation is a different interpretation. It has it that when you make a measurement, it's not that the wave function collapses, but each possible outcome happens in its own universe. So if you have a particle that had a 50% chance of going to the left side of the screen, 50% chance of going on to the right side of the screen, then you're making two universes, one in which the particle went to the right side of the screen and one in which it went to the left side of the screen. The issue is just that we don't see both universes, we only see one of them. So for us it looks exactly the same as if the wave function collapses. So there's no observation that can refute or confirm that those copies in the multiverse actually exist. So why do physicists believe that those other universes exist? I've thought about this for way too long. I've thought about it for so long that I wrote an entire book about it. I think the issue is that they've become lost in maths. Just because there's math first doesn't mean it's real. So this is what's going on with all those multiverses. They have a particular theory, and some of what the mathematics in this theory describes agrees reasonably well with what we observe. And then they conclude that everything that's in the mathematics also has to be real. And I think that's a pretty big leap of faith. It's definitely something that doesn't automatically come out of science. You can assume that it's real. You can do this if you want to, but that would be an unnecessary hypothesis. The same is the case, by the way, if you assume that those other universes are not real. That's also an unnecessary hypothesis. It doesn't help us to describe any kind of observation. So science can't tell you that those copies are real, those other universes with the copies of you, but it also can't tell you that they're not real. So do copies of us exist? Well, you can believe it if you want to. Nothing speaks against it, but nothing speaks for it either. Okay, so this all sounds a little bit, oh, you can make up your mind one way or the other. I want to finish with one example where we can actually answer a question, which is whether particles can think. And just to be clear, by particles, I mean fundamental and elementary particles. Think of an electron, for example. So why would you think that particles can think? Well, this idea has become kind of popular in an admittedly small group of philosophers, but they're very vocal. It's called panpsychism, and it's the idea that everything is a little bit conscious because it contains proto-consciousness. So it's not just human beings or maybe, you know, some particularly smart animal that you might think are conscious, but literally everything, glass, carrots, whatever. But in most cases, you don't really notice it. So the idea is that this explains how consciousness comes about, because if you combine things with this proto-consciousness to something that's large enough, then at some point it can become conscious. Now, if this proto-consciousness isn't a physically real thing, then this is just a weird version of dualism, where you have the physical world and then you have kind of a mental world that is completely disconnected from the physical world. And again, that's something which you can believe in if you want to. There's nothing wrong with it, exactly because it doesn't connect to any observation. So this would be an ascientific idea. But if the consciousness stuff is physically real, and this is what most of the panpsychists actually argue, then it better agree with physics. So let's look at what physics says. This is the standard model of particle physics. Those are all the fundamental particles that we know at the moment. You don't have to count them. I can just tell you that 25 of them. And we have tested this model forwards and backwards. Actually, the greatest problem, so to speak, of particle physicists at the moment is that it works too well. They would rather see it fail, but it's held up extremely well. So what do we learn from particle physics? Well, all those elementary particles in the standard model are defined by their quantum numbers. And what's a quantum number? Well, quantum number, things like the electric charge, that's one that you're all used to. There's also something called a spin, that's like a more complicated version of an angular momentum. And then more complicated things like the weak hypercharge, stuff like this. And they're all just literally numbers, like 1/2, 2/3, stuff like this. And those numbers completely specify the properties of the particles. Now, why is this relevant? Well, it's because if we're trying to calculate what the outcome is of a particle collision, like we do, for example, at the Large Hadron Collider, of which you see an example in this wonderful figure. So what you're looking into the beam axis, so that the protons coming head-on, and then they collide and produce a large number of new particles which end up in the detector, and then you have to reconstruct what actually happened in the reaction, and it has to agree with your theory, and it agrees pretty well with the standard model of particle physics. Now, the thing is, if elementary particles had any other degrees of freedom, any other numbers that you could attach to them than those that are in the standard models, then the outcome of those scattering events would be different. And the reason for this, loosely speaking, is that the standard model is a quantum field theory. So it's a type of quantum theory, basically a complicated type of quantum mechanics. And in a quantum theory, everything that can happen will happen. So if you give those particles more internal states, then you will produce them, and that changes the probability that you will produce them, so it just doesn't agree with observation. So what we conclude from this is that this proto-consciousness can only exist if it has no physical properties whatsoever, in which case it does not explain any observations. Because then you're basically back to the problem of trying to explain how consciousness comes about from combining all those elementary particles to a brain, which is indeed a problem, but this is the standard problem that we have with consciousness. So, do particles think? No, they don't. Okay, so this brings me pretty much to the end, but I want to say a little bit more about why I wrote the book. I wanted to say that physics is so much more than what we learn in school. So the way that a lot of people are introduced in school to physics, it's about magnets or how batteries work or things rolling down inclined planes or maybe nuclear decay, that kind of stuff. And I did a quick Google search for physics icons, and this is what came up. And this gives you pretty much an overview how people think of physics. And I think physics is just much more than this. It is our best tool to find answers to those big existential questions. And I've summarized some of them in my book. And I think I'll leave you with this. Thank you for your attention.
So we are going to have questions. So we've got the online world too. People joining us from all over the world. Oh, we've got a hand straight away. Wait for the mic. We've got some mics coming along. So we'll come to you first because it's very keen. So if you can have a mic straight to that person, individual right at the top. Can you put your hand up again so that the individual can see you? Alana, online. We'll crack on with a question online to begin with.
Yes, so we've had people joining us from all over the world, hundreds of people from Brazil, Yorkshire, Vancouver. I'll start with a question from Garth, and he wanted to know, how do you explain the arrow of time, and is it possible that the velocity of light is not constant, for example, as a function of time and space throughout the universe?
So, so the arrow of time, that's a difficult question to which we have only partly an answer. So I think we understand fairly well why time seems to go differently in one direction than the other. The typical explanation is that it has to do with entropy increase. So entropy likes to increase. It doesn't like to decrease. That's the second law of thermodynamics. And this is the reason why the future looks different from the past. Basically, it's because disorder increases, things break, but they don't unbreak. But this answer only brings up a new question, which is, well, if entropy increases, then why was it small in the past? And we don't know. It's called the past hypothesis, and it literally just states, well, the universe started with a small entropy, but we have no idea why that is or how it would come about. Now about the speed of light, this is a hypothesis that has been looked at, and to my best current knowledge, there's no evidence that the speed of light changes, neither in time nor in space. So there are very tight constraints on it.
Let's go to you, the individual. Go for it.
So I think you said that we're not sure how the universe started, and so if we're not sure how it started, why do a lot of people, like a lot of stuff in pop or science and like science in general, why do a lot of people say that, oh, we know that it started with the Big Bang? And
so I think part of the reason is that the word Big Bang has become used in a rather ambiguous way. So the way that I use it, and I think the way that it was originally used, it refers to this hypothetical first moment in time when the energy density was infinite, or maybe if you don't want to talk about this particular moment, then it's maybe a Planck time later. But it's really this this phase where quantum effects will become important. Now, a lot of people in science communication have used the word Big Bang to also refer to much later phases in the universe, for which we actually do have some kind of evidence, when we had a hot quark gluon plasma, that kind of thing. And this part of the theory is pretty well confirmed. This is what I called the standard model of cosmology. So I'm kind of unhappy with the way that this word has taken on to entirely different meanings. So the way that I've been using the word Big Bang, it refers to this hypothetical first moment in time. Does this answer the question, or did it just make it worse?
We have a show of hands for other questions, so we'll work our way down. So we'll go to yourself first. If we can have the microphone passed to the lady in the middle, then we'll have yourself, the individual here, and then we'll come to the front. Thank you.
Thank you for the talk. It was really good. You mentioned that the rate of expansion of the universe is increasing with, I think you said matter and energy. So how does that work? Does that mean that there's more matter and more energy constantly being created to increase the rate of expansion?
That's a very interesting question. So what I meant was that the rate of expansion depends on the type of energy that's in the universe, and it could be different things. It could be matter, like this stuff, like normal matter. It could be weird matter. It could be dark matter. It could be radiation, like basically light, photons, stuff like this. Or it could be weirder things like dark energy and so on. And all those affect the expansion rate differently, which is why we can, from our observation, try to infer the percentage of those different type of ingredients of the universe. Now, if you're asking about what happened with the energy, it depends on exactly what constituent you're talking about. So if you're talking about matter, then the matter just dilutes. So there's nothing funny going on. So if you take a particular volume and you track the expansion of the volume, then the total matter in that volume just remains constant. It just becomes more thinly diluted, so the density goes down. Now, if you're looking at radiation, like light and stuff, then there's an additional effect which comes into play, which is that the wavelength of the stuff also drops, but the wavelength is proportional to the energy. So the energy density actually drops faster than it does for normal matter. And dark energy has the peculiar property that the energy density doesn't drop at all. So if you want to take this literally, it means that if you expand some kind of volume of space which is filled with dark energy, then the energy in this volume actually increases. And yes, this would mean that energy is actually created out of nowhere. And I know people find this a little bit disconcerting. It's certainly not the way that we're used to talking about energy. You know, why save energy if you can make it from nothing? But energy is actually not conserved in Einstein's theory of general relativity. It's just that it's such a small violation, like where we are. It's so teeny tiny that unfortunately we can't do anything with it.
Lovely. If you want to go for it first.
Thank you. So, science fiction writers like the Alcubierre drive, which is a way of going faster than light. And apparently, that doesn't break any laws of physics, but you've told me that it does.
Well, so the issue with the Alcubierre drive is, how do I explain this without writing down equations? So the Alcubierre drive is actually a solution of general relativity. So what this means is that there is a particular space-time which describes this Alcubierre drive, and yes, it could move faster than the speed of light. The reason this works is that the speed of light limit is just a limit for stuff moving in space-time. It doesn't apply to space-time itself. We actually think that the universe expanded faster than the speed of light when it was very young, and for the Alcubierre drive, it works in a similar way. Instead of moving stuff around in space, you move the space faster than the speed of light. Now, the problem with the Alcubierre drive is that if you look at the kind of matter and energy that you would need to actually create this drive, you need negative energies, and for all we know, those don't exist.
Happy with that answer? Yeah. Yeah, brilliant. Okay, let's take the gentleman at the front, and then we'll take the lady on the left.
Thank you for a great
Anybody
talk.
else who can have hands up? So
Can't wait to read the book.
Oh, there's a lot. There's a lot. Okay, well.
I'd like to ask you, why does mathematics describe the universe so well? Where does it fail? And what are we going to do about that?
Well, so the answer to the first question is, I think no one knows. This is what Wigner was referring to with the unreasonable effectiveness of mathematics. I mean, the standard answer to it is that when we're trying to understand the laws of nature, we're talking about patterns, and mathematics is the language that we use to describe patterns. So in some sense it fits together, but it doesn't really explain why the universe is this way to begin with, right? There's that. Where does mathematics break down? Well, currently we don't have any particular reason to think that there is anything where we can't use it. But then, you know, basically when it comes to science, we've only just begun working on it like a few hundred years ago. So God knows what people will come up with in 100,000 years or something. Maybe they'll find something better than mathematics. But there are certainly particular limits to the mathematics that we currently use. One of them is, for example, this issue with the initial condition. So all the theories that we currently use need this initial condition. You just have to postulate it. There's no way to get rid of it. But it's conceivably possible that one day we'll have a different theory which doesn't need initial conditions. This is one possibility. We're also facing limits of mathematics in the description of chaotic and complex systems. If you think about stuff like nuclear fusion, or actually even weather predictions, where chaos becomes really, really important, we just don't have the mathematics to deal with it.
There's an old saying that if you put a physicist in the RI, you'll be here for an infinite amount of time. But we've only got time for about 3 more questions. So I'm going to take 2 from the audience, and then we'll take the last one from the online world. We'll take yourself, the lady at the front, and then we'll go to the gentleman at the back there. Oh, sorry, sir.
So you spoke about quantum theories of gravity. The 2 leading ones right now are string theory and loop quantum gravity. So out of both of them, which one gives us a better description of the current universe? And out of string theory, like there are infinite possibilities, which one would describe the current version of the universe, in your opinion?
Yeah, extremely controversial question. I'm kind of agnostic about the issue. I've worked on quantum gravity for quite a long time, and I've always looked at it from the perspective of experimental evidence. How can you test it? What prediction would it make? And I think neither of those theories actually makes any useful predictions, let me put it this way. People have made up some models, but to the extent that they could be ruled out, they have been ruled out, so we're none the wiser. Either of those theories has some advantages that have been talked through countless times. String theory has the advantage that it seems to fit together more homogeneously with the particle physics side of things. It's very strong. It literally came out of particle physics. Whereas loop quantum gravity, it continues in spirit Einstein's thought of background independence. But I mean, both of those theories, they're pretty much the same age. They're about 50 years old now, and I think they haven't really led anywhere. So I'm not particularly excited about either of them.
We'll take the question from the lady here who already had a microphone, and then we'll take the last question from the audience in the theatre. The gentleman right at the back there, please. Thank you. Lady, if you want to go first. Yep.
With reference to your point, has physics ruled out free will? Could you say just a couple of words about superdeterminism, which I know your views are considered a little bit controversial?
Yeah, so to give you the brief summary of the chapter about free will, it's no, physics has not ruled out free will. It has ruled out certain ideas about free will. So if you think of what I was talking about with the evolution laws that we have, they are deterministic up to those random quantum events. So you have the time reversible evolution law, in which the future is determined by the past, and then every once in a while you have a quantum jump. And this is, for all we know, how the laws for everything work. So everything, including all the particles that make up our brain, and also including ourselves. Now, does this mean that free will doesn't exist? Well, that depends on what you mean by free will. Personally, I don't like the term free will because I don't find it particularly useful. I actually don't even know what people mean by it. Like, free from what? Free to do what? What's this will? And who's willing it? And what does it mean to will something? And so on. So this is a big rabbit hole that I'd rather not go down. So I like to stick with what we know about the laws of nature. There are certainly people who have put forward definitions for free will which are perfectly compatible with what we know about the laws of nature. Now, superdeterminism, this is a particular modification of quantum mechanics in which the measurement of the wave function is actually time reversible. So it replaces this collapse or the reduction of the wave function with the physical process, and it has the big benefit that it's local. So it's not in as much conflict with Einstein's theory of general relativity. Einstein, as you certainly know, never really liked quantum mechanics because it had this spooky action at a distance, and superdeterminism is the only way we know to get rid of this. Superdeterminism has historically been meshed together with the question about free will because it violates an assumption that has been called the free will assumption. And what this assumption means is basically that the state of the system which you prepare, that you're trying to measure, is correlated with the setting of the detector that you use to later measure the system. Now, I honestly don't know what people think this has to do with free will, because you don't even need any human being or something to set the setting at a detector. It could be done by an apparatus. Actually, in many examples that people have looked at, it's actually done by a computer. So I think it's just a historical accident that it has become called the free will assumption.
And the last question from the in-theatre and the audience. Can we have the gentleman at the back there?
So I was wondering, could the expansion of the universe eventually come to an end and then it actually starts reversing, so it starts collapsing on its own, and so it's like a cycle?
Yeah, so this is the idea of the cyclic universe. There are different scenarios for this. So I didn't actually talk about the end of the universe, but it has a similar problem as our theories for the beginning of the universe, which is that our extrapolations just can't be tested. So with the end of the universe, the problem is a little bit different, which is that if we take the theories that we have well tested today, then you extrapolate them into the far future, there could be very small differences in the evolution or to what we currently think it is, which would become very, very significant in the far future. A typical example for this is dark energy. So the current expansion of the universe is entirely dominated by dark energy. And if you assume that dark energy remains constant, then you can calculate what happens in the universe will expand forever. The acceleration will get faster and faster. But maybe dark energy actually becomes smaller. And how will we know what's going to happen in 100 billion years or something like this? And if you make an assumption about this, you can basically do anything, in your mathematics at least.
And on that note, I think we'll go back to the online audience who have been patiently waiting for the last question of the evening. So Alana, do we have one last question from the online world?
Yes, so the online world's been debating everything from breaking the laws of thermodynamics to how do we access the past if it does exist, and if we could access it, could we change it? But what I will actually end on is the question of what existential problem would you like to solve the most? So this huge debate that's happening in the room and online, if you could solve any of these questions or problems that you're working on, which would be the pinnacle of solution?
Yeah, so for me, it's the error of time. So as I said, we understand part of the story, but we don't really understand the whole story. And I personally find this explanation with the increase of entropy incredibly unsatisfactory. I don't think it really works. And then I would really want to have an answer to this, like what's going on with the entropy in the early universe.
Can we please give a massive round of applause to Sabine Hossenfelder? Thank you.
In December 2020, the Arecibo telescope, one of the largest and most iconic astronomical instruments in the world, collapsed. This 57-year-old megastructure not only made incredible scientific discoveries over its lifetime, it was also an emblem of humanity's interest and curiosity about our place in the universe. Its loss was felt across the world. The National Science Foundation, who owns the observatory, recently released their report to Congress on the cause of the failure and the events leading up to it. Why was this telescope so important? How did it work, and why did it fail? I'm Grady, and this is Practical Engineering. In today's episode, we're discussing the Arecibo telescope collapse. The same way we observe visible light from celestial objects using our eyes and optical telescopes, we can also take advantage of other parts of the electromagnetic spectrum in astronomy. Most of the gamma rays, X-rays, ultraviolet, and infrared portions of the spectrum are blocked out by the atmosphere, but long wavelength radio waves are not. A radio telescope is basically an antenna that can tune in to some frequencies of electromagnetic radiation that emanate from celestial objects. These radio waves can be quite faint, complicating the task of separating them from the background noise. You essentially have two options to get high-quality radio astronomy data: more time or more space. The longer you focus on an object, the more resolution you get. But there's only so much time. To speed up observations, you can also gather radio waves from a larger area and focus them into a clearer signal. Arecibo took that strategy to the extreme with its 305-meter or 1,000-foot diameter dish, the largest in the world until China's half-kilometer FAST scope took the title in 2016. Located on the Caribbean island of Puerto Rico, the Arecibo Observatory was designed and constructed in the 1950s and 60s as a Department of Defense project to detect nuclear warheads in the upper atmosphere. The National Science Foundation took over the facility in 1969 to use it for more peaceful endeavors, with the help of a few managing partners over the years. A big part of Arecibo's mission is education and outreach programs to engage the public's interest in astronomy and atmospheric sciences. If you grew up in Puerto Rico, you almost certainly visited this incredible facility on a field trip, or 2 or 3. The most iconic part of the observatory was the massive radio telescope. Not only could it receive the faintest of radio signals, it could transmit them as well, allowing Arecibo to work as a celestial radar. It could send out radio signals and measure the returning echoes from nearby objects in space, including planets and asteroids. Arecibo facilitated some of the most exciting astronomical discoveries of our age, including the Nobel Prize-winning observation of binary pulsars, providing the first evidence of gravitational waves. The telescope's dish was constructed inside an enormous circular sinkhole. Although it looked solid from a distance, the reflector was a series of aluminum panels carefully suspended on steel cables. Because the dish was fixed to the Earth, it was constrained to point at whatever part of the sky happened to be overhead. Radio telescopes can be used during the day and night, so there's more sky to look at over the course of a day or year, but a telescope that can't steer is still pretty useless. The designers of Arecibo had a pretty clever solution to the problem. Rather than using a parabolic shape for the dish that would focus everything to a single point, they chose a spherical curve. Spherical reflectors don't perfectly focus all the incoming rays. That might sound like a bad thing since you want to gather and focus as much signal as possible across the entire dish. The beauty of a spherical reflector is that by changing the position at which you measure the reflected waves above the dish, you're measuring those waves from different parts of the sky. You can essentially steer the telescope by choosing where to receive radio waves above the dish, allowing you to focus on various objects and track them as the Earth rotates. Focusing those waves to a narrow area above the dish doesn't do much good unless you have a receiver up there to collect and measure them. The Arecibo telescope was designed with a triangular platform suspended by steel cables above the dish to support the various instruments used to gather radio signals. To keep the platform aloft, 3 reinforced concrete towers, named for their positions on a clock of 4, 8, and 12, supported each group of cables. There were originally 4 cables for each corner of the platform, 3 inches or 8 centimeters in diameter. Big cables. Additional cables, called backstays, were connected to anchorages behind each tower to balance the horizontal forces. similar to the way suspension bridges work with their towers and abutment anchorages. Initially, the telescope used line feeds, elongated receivers that could gather signals within the focal line of the spherical dish. But they could only measure signals within a narrow bandwidth, so line feeds would have to be swapped to change the frequency of the telescope. Upgrades in 1997 included the addition of the Gregorian dome that uses 2 additional reflectors to focus radio waves. This dome allowed telescope operators to observe a much wider range of radio frequencies. But this Gregorian dome didn't just add capabilities, it also added weight, lots of weight, about 50% of the original platform. All of this extra load required some more support, so 2 auxiliary cables from the platform to each tower were added, plus more backstays to balance the load. In addition to that, the dome was far more sensitive to tiny movements. You can imagine the stiffness and rigidity of a gigantic wind-catching dome suspended in the air by narrow steel cables. Not an ideal structural arrangement for a sensitive instrument. To compensate, 3 tie-down cables were added, 1 for each corner of the platform, increasing the forces even further. A laser ranging system could communicate with hydraulic jacks to carefully adjust the tension in these tie-downs and keep the platform perfectly stable, within the precision of a millimeter. The telescope's last few years were pretty rough. The 2017 Atlantic hurricane season sent 2 massive storms, Irma and Maria, across Puerto Rico. Maria was one of the strongest storms ever to hit the island and caused nearly 3,000 fatalities and close to $100 billion in damage. Arecibo wasn't spared from that devastation. It suffered a broken line feed that fell from the instrument platform and crashed through the dish, among other damage. More consequential than hurricanes, though, Arecibo was slowly losing its funding. The National Science Foundation had been trying for years to divert Arecibo funds to newer projects. In 2018, the University of Central Florida stepped up to take over the management and funding of this observatory, not knowing what was soon to come. Only a few years later, in August 2020, one of the newer auxiliary cables on Tower 4 broke free from its socket unexpectedly in the middle of the night. As the cable failed, it crashed through the reflector dish, tearing a gash through the aluminum panels. These sockets, called spelter sockets, used to attach the cables to the tower, are a common way to terminate wire ropes and cables, but they have to be installed correctly. You have to broom the end of the cable, making sure that every strand is separated from the others, clean them meticulously, then carefully pour molten zinc into the socket to create a permanent wedge that only gets tighter with more tension. If done properly, the termination should be stronger than the cable itself. In other words, there's no good reason a cable should ever pull out of a spelter socket, and yet this was not the first incident of cables slipping in their sockets at Arecibo. Maintenance staff at the observatory had been concerned about the problem for years. This failure was the beginning of the end of the telescope, though we didn't know it yet. The damage from the failed cable was significant, but the engineers brought in to assess the structure believed that it could be repaired. The suspended platform was designed with some redundancy, so losing a single cable wasn't necessarily catastrophic. Managers put a temporary stop to the science at the facility while a remediation project could be installed, but it had to be designed first. As a first step, engineers developed a structural computer model of the platform and towers to evaluate options for repair. One nice aspect of cable-supported structures is that you can estimate the tension in each one just by looking at it. All cables sag under their own weight, following a curve called a catenary. The more tension in the cable, the tauter it becomes, and so the less it sags. If you know the weight of the cable, you can use the catenary equation with the measured sag distance to estimate cable force fairly accurately. A sag survey was conducted at Arecibo using lasers, and this is how the structural model was calibrated. To make sure the model could predict how changes in forces would affect the structure, the engineers performed some pretty clever validation as well. Since they had measurements of the instrument platform before and after the first cable failed, they could remove that cable in the model and compare the predicted behavior of the platform to what actually happened. When the first cable failed, that corner of the platform dropped by 2.5 feet, or about a meter, and the model was able to predict this within a couple of inches. While all this design was taking place, further trouble was just around the corner. In November, only 3 months after the first cable broke at Tower 4, a second one failed. This time it was one of the original cables installed in the 1960s. It didn't pull from its socket, but simply broke. And it broke at a force well below what it should have been able to handle. About 62% of its rated strength, to be precise. The falling cable again damaged parts of the telescope, and again the platform remained standing. However, optimism about the structure was quickly declining. The question went from how do we fix the telescope to can we fix the telescope? And there were differing opinions. The engineers used the structural model to evaluate options that could relieve the tension in the remaining cables and reduce the possibility of a complete failure. They could cut the broken cables, since they're pretty heavy and not doing anything useful anymore. They could move the Gregorian dome so the other towers were holding more of its weight. They could loosen the backstays, causing the towers to lean inward by 18 inches or half a meter. And of course, they could add some temporary cables at Tower 4 to take up some of the weight. All of these options showed reductions in the forces carried by the remaining cables. But the problem was figuring out how to do the work safely. At this point, they had 2 failures, both well below the specified breaking strength of the cables. Not only had the telescope lost its structural redundancy, but the engineers also didn't trust the strength of the remaining cables, and for good reason. Crews couldn't access the site due to the risk of another cable failing, but nearly all the options to relieve the load on the cables would require having personnel on the platform and towers. One of the engineering firms working on the problem suggested some last-ditch efforts to save the structure. After that, they could perform proof tests remotely using the tie-down jacks to check if the remaining cables had at least 10% extra strength. If the engineers could gain some confidence in the strength of the remaining cables, crews might be able to enter the site and implement further measures to save the structure. However, no one could get comfortable with the risks of the helicopter work or proof testing the already distressed cables. It's a tough thing to say when such an important and iconic structure is still standing that there's no path forward to repair. This quote from the engineer tells the whole story. It is unlikely any of these methods will yield sufficient reductions without placing crews in jeopardy. Although it saddens us to make this recommendation, we believe the structure should be demolished in a controlled way as soon as pragmatically possible. They wouldn't get the chance, though. On the morning of December 1st, a third cable at Tower 4 broke, starting a chain of events that would quickly collapse the structure. Amazingly, one of the observatory staff was flying a drone at the top of the tower when it happened, capturing this incredible footage of the event. It happens almost instantly. 2 of the main cables are already clearly in distress when the video starts. All the chipped paint is from individual strands of the cable failing. Observatory staff could hear these breaks and knew what was likely imminent, which is why the drone was up there in the first place. The third cable snaps, and the remaining cables, forced to bear the additional load, quickly follow. The drone turns around to reveal the platform crashing into the side of the dish. The observatory also had a GoPro set up in the control room that captured the failure. You can see the cables let go from Tower 4, the platform swinging downward, the supporting cables crashing through the suspended catwalk, and the top section of Tower 4 breaking off from the unbalanced force of the backstays. All 3 towers suffered failures, major portions of the dish were destroyed, and the platform and instruments it supported were a complete loss. Several buildings, including the visitor center, were damaged by falling debris. Thankfully, even though there were people on site during the collapse, the engineers had established safe zones away from the structure, and no one was injured. Several forensic investigations are still underway to examine the causes of these failed cables. Those results could be years away, so we don't yet know for certain why the first 2 cables gave way, when they should have had more than enough strength to carry the load. Engineers involved during the event suggested the first cable to fail likely was not fabricated correctly. Whether the spelter sockets were installed in the field or a shop, there are a lot of details required to do it properly, and it's certainly possible that something was missed. And once those sockets are installed, they are difficult to inspect. As for the second cable, the engineers suggested a likely failure mode to be corrosion of the steel. The cables were painted regularly and reportedly had a dehumidification system that could blow dry air between the strands, although those systems usually require an airtight sleeve around each cable. Even so, Arecibo sat nearly 60 years, only a short distance from the northern coast of Puerto Rico, and exposure to that salty sea air could have accelerated the demise of the main cables. Another element worthy of scrutiny is the factor of safety used in the original design. This is the quotient of a structure's demands and its strength. The whole point of a factor of safety is to accommodate uncertainty. We predict the demands on a structure, we compare them to the strength, we recognize that there might be extra forces or less strength than expected for a variety of reasons outside our control, so we give our structure some margin. The Arecibo suspended platform cables were designed to have a factor of safety of 2, meaning they were twice as strong as the expected static loading from the platform. That might seem like a lot, but consider that elevator cables use a factor of safety of 11, and many bridges use safety factors above 3. In aerospace engineering, where weight is critical, they do tons of modeling and testing to build enough confidence in designs to get their factor of safeties down to around 1.5. Arecibo was a unique facility, unlike any other structure in the world. It didn't go through a rigorous structural testing program, and it was designed before computer modeling could be used to accurately characterize all the static and dynamic forces it could experience. I think it's worth considering whether the structure should have been designed with a little extra margin, especially considering the possible circumstances in which that margin would be required. A cable failure is a violent event. All the load the failed cable was carrying doesn't just redistribute itself to the other cables evenly and gently. The dynamic loads that occur as the structure shakes and vibrates can be significantly higher than the static loads. It wouldn't be surprising at all to find out that the peak stress in the remaining cables on Tower 4 actually did exceed their rated strength when that first and second cable broke, even if only for an instant. Despite the collapse, Arecibo Observatory is not closed, and science continues at the other facilities on site. As of this writing, crews are still working to clean up the debris from the collapse, and the National Science Foundation is holding workshops to discuss the future of the site. I hope eventually that they can replace the telescope with an instrument as futuristic and forward-looking as the Arecibo telescope was when first conceived. It was an ambitious and inspiring structure, and we sure will miss it.
Close now with a look at a bit of stellar evolution for the next 3 or so minutes from the A Cappella Science Channel. And one thing to note is in the bottom, the box at the bottom, what a Roche limit is, if you've not heard of that before, because it is actually mentioned in the video. It's actually the distance from a body within which a second body held together only by its own gravity will disintegrate because the first body's tidal forces exceed the second body's self-gravitation. So if you've got, say, for example, the Earth and the Moon, how close can you bring the Moon before Earth's gravity will pull it apart? So in other words, the Moon can't hold itself together and will pull it apart. So in the case of the Earth and Moon, it's only 1.5 Earth diameters, roughly. So in other words, that's because it's measured from the centre of the Earth, that means it's about 1 Earth away. If you brought the Moon in that close, Earth would rip it apart, right? In the case of Saturn's rings, they're inside the Roche limit. So in other words, they've already been ripped apart. But it applies to any two celestial objects, not just planetary ones. So this goes for about 3 minutes or so. And with that, we'll see you at the main meeting. We'll close tonight. Thank you.